So I'm going to talk about our work on efficient verifiable range and closest point queries in zero knowledge. And this is joint work with Brown alumna Olia Orimenko, who's now a researcher at Microsoft Research, and my advisor Roberto Tomasi at Brown. So with the advent of cloud computing, both corporations and individuals adopt cloud services to outsource a large amount of data and computations. Now, however, the fact that the data owner is not in possession, physical possession of the data anymore, raises obvious integrity issues and challenges. But that's not all. Moreover, often third-party clients are allowed partial access to this outsourced data, which raises privacy issues. So traditionally, this cloud databases has been studied in the following three-party model. So a trusted owner of the data pre-processes the data to generate some tokens specific to the data, and it outsources the data and the tokens to this cloud provider. And it also generates a short, succinct information about the data, which it posts publicly, which is called PKD, and it goes offline from this whole phase. And later, when clients want to query the data, it interacts with the server to ask questions about the data and get the corresponding answers. But because of the integrity issues, traditionally the threat model that has been studied is the adversarial server, which means the client does not necessarily believe that the server is giving the correct answer. So the client also expects a proof of the answer. And then the client will be able to verify this proof against this short public digest information that has been posted. So, but in this setting, and there has been a huge amount of work in this setting, and many primitives and data structures have been developed in this technique. But the problem with this technique is the proofs often reveal way more information that can be inferred from the answer itself. So to give you a very quick example, Merkle hash tree, which is one of the most widely used data structures in this setting, if you think about it, let's say the owner wants to authenticate this data items, which are the leaves of the Merkle tree. So it generates this Merkle tree on top of it. The Merkle tree is the authentication token that it sends to the server, and this succinct digest is the root of the Merkle tree, which is posted publicly. Now at a later point, when the client wants to query for a data, say if is X in my database, the proof of this answer is basically the sibling path, which are the yellow nodes in this graph. But as you can see, the sibling path, the height of the sibling path itself reveals the number of elements in the database. But that's not all. When the data is stored in an order, so it basically also reveals the rank information of the data that is stored in the database. So this is just one of the most widely used techniques, and it leaks a lot of information. Just to give you an example that these data structures are not privacy preserving. So is this a problem? Yes, this is not just a theoretical risk. So there have been many practical attacks demonstrated in this threat model. Sorry. Right. Yeah, so there have been, so some of these applications include DNS security, selective release of medical health records. We have heard a lot of talks about health records today. But to give you a concrete example as a warm-up, think of an organization which stores its email records of its employees on a cloud server. Now, when in case of some malicious activity, sometimes this third-party auditor is given partial access to this record. So for example, this auditor is given access only to 4th to 14th April because there was some suspicious activity going on, and it is allowed given access token to access only that part of the record. Now in this case, since the record is not coming from the organization itself, the auditor needs a proof that it has not been tampered, the records have not been tampered with. But additionally, because this is email records and it's privacy sensitive information, it's important to not, so when you have to also give a proof that the answer is complete, meaning that the server is not withholding any record that it should have returned. But the proof should not be revealing any information beyond this range of data, 4th to 14th April. Okay. So to study this model formally, we initiated the study of this formal model where basically it is the three-party model with this additional setting of privacy against the client. So if you recall the three-party traditional model, there was only one adversary, which is the server. So in this model, even the client can be adversarial, meaning that the client does not trust the server about the integrity of the proof, but the client should not learn or should not be able to infer more information about the query answer from the proofs than from the answer itself. So, if more formally it is like a zero knowledge privacy, meaning the proofs should be simulatable, but if you did not understand what that means, never mind. It basically means that the proof should not reveal anything beyond the returned answer. Okay. So, the goal of designing this kind of primitives is threefold. Obviously, it should be maintaining integrity and privacy in a provable way. But another very important aspect in this primitives is that it should be time and space efficient for all the parties involved. Otherwise, one of the major benefits of adopting cloud services, which is scalability, is defeated. So, okay, so with that I have talked about the motivation and the construction. Now let's jump into the work that we do in this paper. So in this paper we are working with range queries. So what meaning that the data store we consider is a data store of key value pairs, but the keys are you can think of them as binary strings. They're coming from a totally ordered universe, and the query here is a range query, meaning the client asks return me all the keys from a given interval A to B. So the server should respond with the correct key value pairs and the proof that the answer is complete. If you think of the email record, it's just that was an example of range query. And this problem has been studied by Ostrowski, Rakov, and Smith in a slightly stronger two-party model in 2004. But this result was mostly of theoretical interest, and there has not been much progress after that. So, okay, so let's take a moment and try to understand why this is difficult to do. So think of this tiny database, which is our toy database, as a database of email records, and corresponding to the query of 4th to 14th April, the marked highlighted records should be returned to the client. Now, the client needs to know that these records are authentic, but it also needs to know that no record has been withheld. So, there are techniques that you could employ like Merkle hash tree, which will not be privacy preserving. But one obvious privacy preserving way to go is maybe the owner signed all the keys that are present in the database and also all the keys that are not present in the database, since the universe is known already. So for these empty spaces like 4th April, there's no record corresponding to that. The owner could have generated a special signature saying 4th April bought, nothing is there. But obviously this is privacy preserving, but this will be immensely inefficient, because that means the answer is basically proportional to the number of keys in the entire range and not the number of records that are actually present in the database. So this is sort of the challenge why naive solutions do not work very quickly. So what is our idea? So very at a high level, the overview of our construction is use signature elements for the members that are present in the database. That's very easy to do. But the challenging part is how to prove that the portions that are empty, in a sense, without revealing anything else. And for that, we use hierarchical identity-based encryption. So I will quickly recap what that means before we go to the construction. So hierarchical identity-based encryption, this was also in one of the keynote talks today. So it basically allows one to efficiently derive encryption and decryption keys, respecting the access control based on a hierarchy of identities. So the identities are public identities, which you can think of arbitrary binary strings. Now the hierarchy of identities, you can think of a full binary suffix tree. Okay? So what is the property? Like in any encryption scheme, a message can be encrypted for any public ID by anybody, but whoever owns the secret key corresponding to that public ID will be able to decrypt it. So if you think of the hierarchy of ID trees of depth 3, the ID for a node 00 will be its two children, 001 and 000. Okay? Now the additional property here is that a node can derive secret keys for all its descendant IDs, which means if you encrypt a message for a particular public ID, of course, that person with that secret key will be able to decrypt it, but it will be able to decrypt any message intended for his children also, but nothing beyond that subtree. Okay? So in an example, quick example, if somebody had the secret key for 0, this public ID, it will be able to derive secret keys for all these children, okay, but nothing beyond that subtree. Okay. Now let's step back to range queries and see what we can do. So with our toy example, let's say these are the binary strings which are the keys of the data store, okay, 0 to 15, and the ones marked in yellow are actually the elements of the database. Those key value pairs are present in the database. So implicitly, you can think of this binary suffix tree, where if this is a full binary suffix tree of height k, where each, yes, oh, okay, where each bit length is k bits. Okay. So the idea of doing this is basically the owner can prune the red paths, which are the paths from the leaf to the root of the member elements, and this it will be left with a forest. And this forest, take the roots of the forest, which are these pink nodes. Okay, so at the setup phase, the owner will basically generate signature for all the member elements and will set up a Hive scheme and generate secret keys for the roots of this forest. And then the owner goes offline. Now in the query phase, let's say our typical example 4 to 14, in the first phase of the query, the server will return the signature of the member elements. Now notice that, okay, let's quickly talk about what is a canonical covering or CC. So a canonical covering with respect to a range AB is basically the minimal set of nodes that cover it completely. So in the interest of time, I'm going fast over this, but catch me offline if you want to talk about it. But this is unique with respect to a height of a tree and a given range. So basically, once the member elements are returned, that uniquely breaks up the queried range into a bunch of subranges, and the canonical covering for the subranges can be computed independently by the client and the server. So the bold nodes here, the client can encrypt messages under those IDs, and the server either possesses those secret keys from the owner, or it can derive it by the property of Hive, and it can prove that those and decrypt the nonces. Basically, that's the challenge response phase. And this is the complexity is proportional except with the k-square factor to the answer size, which is good. And this is a comparison with the ORS scheme, which was not even zero knowledge. The proof size is much better and it's stateless and so on. So I'm going to quickly go to the implementation that we have done. So we have implemented it on both synthetic and real data. So as you can see, you can imagine if the data is clustered, if the keys are clustered and there are long empty ranges, that's good for all the parties, because you will be able to cover it with a node which is very higher up in the hierarchy of the tree. Otherwise, it's bad, and that is the result we see here for different. So D dollar is basically a completely random database, and D16 is database where each cluster is of 16 keys, and DN basically one huge cluster. So as we see, as you increase the clustering level, the performance improves for all the parties. And this is a chart of the variance, and we also implemented it on real data sets. One was the Enron email data set, and another was the Boston taxi data set. We noticed that the Boston taxi data set showed more clustering property, so therefore it showed much better performance than the Enron email data set. And finally, to conclude, so we presented and experimentally evaluated this 1D range queries, and as an application, we show how to do closest point queries, which is basically very simple. The answer size is constant in that case. And two interesting open directions that we did not address in this paper are to extend this to multidimensional data sets and also to handle dynamic data sets. Yeah, and that's all. And thank you for your attention. And I'll be happy to take questions.